Surely it has happened to you. You buy a new car, you read the technical sheet with hope, and you see a figure that seems like a dream: 4 liters for every 100 kilometers. You go out on the road, you drive with the smoothness of a Tibetan monk, you stroke the accelerator as if it were made of glass, and when looking at the onboard computer, reality hits you in the face: 7 or 8 liters. At that moment, you feel that you have been deceived. And the truth is that, technically, they have an explanation, but the result for your pocket is the same. So, let us begin. Reason 1. Clogged or leaking injectors. The injector is possibly the most precise piece of engineering in your entire engine. We are talking about a component that must open and close thousands of times per minute, delivering an exact amount of fuel measured in milligrams. But the problem is not just how much fuel enters, but how it enters. For gasoline or diesel to burn efficiently, they must mix intimately with oxygen. For this to occur, the fuel must be atomized. Imagine the atomizer of an expensive perfume. It creates a cloud of droplets so fine they look like gas. Now imagine an old garden hose that leaks. If your injector is dirty, it stops being an atomizer and becomes that hose. Injectors work with extremely high pressures, especially in modern direct injection engines. Over time, sediments present in the fuel, carbon deposits, varnishes, and microparticles, settle in the injector nozzle. This causes 2 catastrophic scenarios for consumption. Partial clogging. The orifice becomes smaller or deformed. The cloud of fuel comes out deflected or with droplets that are too large. These large droplets do not have time to burn completely during the combustion stroke. The result is wasted energy that exits through the exhaust in the form of unburned hydrocarbons. Your car is, literally, throwing money out the tailpipe. Dripping injector that does not close. This is the most serious scenario. Due to dirt on the internal needle, the injector does not seal hermetically when it should be closed. It continues to drop fuel into the cylinder even when it is not the time for the explosion. This not only increases consumption massively, but it can wash the cylinder walls, removing the lubricating oil film and causing premature engine wear. Reason 2. The airflow sensor, MAF, and the pressure sensor, MAP. Your car has a central brain called the ECU, Electronic Control Unit. Like any brain, its decision-making ability depends entirely on the information it receives from its senses. In this case, its most important senses for fuel savings are the MAF, Mass Airflow Sensor, and the MAP, Manifold Absolute Pressure Sensor. The MAF sensor is usually located just after the air filter. Its job is to measure exactly how many grams of air are entering the engine per second. It uses a platinum wire or a thin film that is electrically heated. As the air passes, it cools that wire. The ECU measures how much current it needs to keep the wire hot and, through complex mathematical calculations, determines the mass of air. The problem is that this wire is extremely sensitive. If the air filter lets microparticles of dust pass through, or if engine oil vapors condense on it, an insulating layer is created. Imagine trying to feel the wind wearing 3 pairs of gloves. The sensor becomes slow, or a liar. If the MAF tells the ECU that less air is entering than actually is, the mixture will be lean and the car will lose power, forcing you to step on the pedal more. But the most common thing is for the sensor to fail upward, or for the ECU, when in doubt, to enter a protection mode by enriching the mixture to prevent the engine from overheating. The result? Consumption that rises 10 or 15% without any fault light coming on the dashboard. In many modern cars, the MAF is supplemented or replaced by the MAP sensor. This measures the pressure or vacuum inside the intake manifold. It is vital for calculating the engine load. If this sensor fills with carbon, something very common in diesel engines due to the EGR valve, its readings will be erratic. If the ECU believes the engine is under a lot of load because the MAP sensor is clogged, it will inject more fuel than necessary. It is as if the car thinks you are climbing a mountain when you are actually on flat ground. You are burning gasoline for a battle the engine is not fighting. Reason 3. The saturated air filter. It is often said that the air filter is the lung of the car, but I like the marathon runner analogy better. Try running 10 kilometers, breathing through a straw or with a mask full of mud. You will get tired much sooner, your heart will beat faster, and you will need much more energy to cover the same distance. That is exactly what happens to your engine when the air filter is saturated. An internal combustion engine is, in essence, an air pump. To produce power, it needs to suck in air, compress it, and mix it with fuel. If the filter is blocked by dust, pollen, insects, or urban pollution, the engine has to perform additional mechanical work just to suck the air through that barrier. This extra effort is known as pumping losses. In old carbureted cars, a dirty filter was catastrophic because the lack of air caused the mixture to enrich automatically, triggering brutal consumption. In modern cars with electronic injection, the ECU detects that less air is entering and reduces the amount of gasoline to keep the mixture balanced. So, why do we spend more? The answer is in your right foot. By having less air available, the engine produces less power. Since the car runs less, you, unconsciously or consciously, step on the accelerator more to maintain cruising speed or to perform an overtake. By stepping on it more, you open the intake butterfly valve more, but since the system is inefficient due to the filter restriction, the engine operates outside its zone of maximum thermal efficiency. Not all filters are the same. A poor quality filter may look clean but have inadequate porosity that restricts the passage of air from day one. Even worse is when a filter gets damp. If you live in a very rainy area, or if water has entered the filter box, the paper fibers swell and the air passage is drastically reduced. Reason 4. Spark plugs in poor condition and deficient coils. The thermodynamic efficiency of an internal combustion engine depends directly on the quality of the transformation of chemical energy into mechanical energy. In this process, the ignition system acts as the orchestra conductor that decides the exact moment and intensity with which that force is released. When we talk about spark plugs in poor condition or coils that have lost their insulation or conductivity capacity, we are facing one of the most silent and constant fuel drains a modern vehicle can suffer. To understand why a worn spark plug ruins fuel economy, we must visualize what happens inside the combustion chamber. The air and gasoline mix in a ratio that ideally seeks chemical perfection, but that mixture needs an external catalyst to react. The spark plug must not only fire a spark, but it must generate an electric arc, hot and stable enough to propagate a uniform flame front. When the spark plug electrodes wear out due to the passing of kilometers, the distance between them increases. This increase in space forces the coil to make a greater effort to jump the vacuum, which often results in a weak, erratic spark, or in the worst case, none at all. A weak spark fails to burn the entirety of the injected fuel. This generates what technicians call incomplete combustion. If part of the fuel does not burn, it does not produce thrust on the piston, which means the engine must perform more cycles and consume more liters to maintain the same speed or power. Basically, the user is paying for gasoline that comes out raw through the exhaust, wasting money on every failed explosion. Furthermore, the ignition coils play a crucial role. With the extreme heat of the engine bay, the internal components of the coils degrade. A deficient coil may not fail completely, but it can present current leaks or inconsistent voltage delivery. This translates into micro-jerks that are sometimes imperceptible to the average driver, but that radically alter the injection map. The car's computer, upon detecting that combustion is not efficient through other sensors, tries to compensate by adding more fuel, entering a vicious cycle of high consumption. Reason 5. The oxygen sensor lambda probe. The oxygen sensor, commonly known as the lambda probe, is the final watchdog of engine efficiency. Its function is to measure the amount of oxygen remaining in the exhaust gases to inform the control unit if the mixture is rich or lean. However, there is a technical phenomenon very dangerous for the owner's pocket, the slow or lazy oxygen sensor. An oxygen sensor has a limited useful life. Over time, it becomes coated with deposits of carbon, lead, or burnt oil residues that act as a thermal and chemical insulator. When this happens, the sensor does not stop working completely, so the vehicle's computer does not detect a total failure and does not turn on the warning light on the dashboard. Nonetheless, the sensor's response speed decreases drastically. Instead of oscillating rapidly between rich and lean mixture values to maintain balance, the sensor gets stuck on a slow reading. The main problem lies in the fact that most of these sensors, as they age, tend to report a falsely lean reading. The computer, believing that the engine has little fuel, orders the injectors to remain open for a longer time. This misinterpretation can increase fuel consumption by up to 20%. It is a frustrating situation because the vehicle seems to operate normally, but the user notices that visits to the service station are increasingly frequent. Reason 6. The EGR exhaust gas recirculation valve and the vacuum system. The exhaust gas recirculation valve, known by its acronym in English as EGR, is a component originally designed to reduce nitrogen oxide emissions. Its operation consists of reintroducing a part of the already burned exhaust gases into the intake to reduce the combustion temperature. Although it seems contradictory to put trash into the engine, when this system works correctly, it improves thermal efficiency under certain partial load conditions. The conflict arises when the valve fills with soot and remains partially open or closed. If the EGR valve gets stuck in the open position, the engine receives exhaust gases when it should not, such as during idling or heavy acceleration. This causes an entry of unaccounted air that makes the mixture lean and generates instability. The driver feels a lack of power and, to compensate, steps on the accelerator more, which triggers fuel consumption immediately. On the other hand, the vacuum system that usually controls both the EGR and other engine actuators is a common source of invisible leaks. Modern engines depend on a network of rubber hoses that, over the years, become brittle and develop microscopic cracks. These vacuum leaks alter the stoichiometric ratio, which is the ideal proportion of 14.7 parts of air to 1 part of fuel. Reason 7. Incorrect tire pressure. Rolling resistance is probably the most underestimated enemy in the fight for energy efficiency. Tires are the only point of contact between the machine and the ground, and their condition determines how much of the energy produced by the fuel is wasted in the form of heat and deformation. When a tire does not have the proper air pressure recommended by the manufacturer, its structure deforms excessively when turning. This constant deformation requires energy to occur, energy that comes directly from the gas tank. A tire with low pressure increases its contact surface with the pavement, but not in a way that is useful for grip, rather in a way that generates unnecessary drag. The rubber, being softer than it should be, undergoes a more severe hysteresis process. This means the material heats up while it bends and stretches in each rotation, wasting power that should be used for momentum. Automotive engineering statistics suggest that a drop of barely a few pounds in pressure can raise fuel consumption significantly because the friction coefficient increases drastically. Reason 8. The thermostat stuck in the open position. The internal combustion engine is a thermal machine that needs to operate within a very specific temperature range to be efficient. This range is usually between 90 and 105 degrees Celsius depending on the design. The person in charge of regulating this balance is the thermostat, a small valve that controls the flow of coolant to the radiator. A very common and dangerously ignored failure is when the thermostat stays stuck in its open position, allowing the water to circulate freely to the radiator even when the engine has just started. When this happens, the engine takes an eternity to reach its operating temperature, or even worse, it never reaches it if the vehicle is driving on the highway or in cool climates. It might seem that a cold engine is a good thing to avoid overheating, but the reality is that an engine working below its ideal temperature is a gasoline devourer. The car's computer, upon receiving the signal from the temperature sensor that the block is cold, assumes that the vehicle is in the warming up phase. To compensate for this, the control unit orders an extremely rich fuel mixture, injecting much more gasoline than necessary to try to generate heat quickly and maintain idling stability. Reason 9. The use of air conditioning and electrical load. All the comfort and technology we enjoy inside a modern automobile have a price that is paid at the fuel pump. The alternator and the air conditioning compressor are mechanical devices that are coupled to the engine by belts. For these components to turn, the engine must deliver a part of its available power, which increases the load and therefore the consumption. The air conditioning is the most voracious consumer of parasitic energy. When the compressor engages, it represents a considerable mechanical effort that can subtract between 3 and 8 horsepower from the engine, depending on the size of the system. In low-displacement vehicles, this impact is much more evident since the engine must perform a proportionally greater effort to maintain speed while dragging the compressor. The indiscriminate use of air conditioning in the city, where the engine already suffers from constant stops and starts, can raise fuel expenditure significantly. It is not just about the energy needed to cool the passenger compartment, but about how the engine management system must raise the revolutions per minute to prevent the car from stalling under that extra load. Reason 10. Aerodynamics and unnecessary weight. The efficiency of a vehicle in motion is a constant battle against air resistance and the inertia of mass. Aerodynamics is not a concept exclusive to Formula One racing cars, but a physical reality that affects any object traveling at more than 50 kilometers per hour. As speed increases, the air becomes a much denser barrier and harder to pierce. If the original design of the manufacturer is altered by external elements, the drag coefficient increases exponentially, forcing the engine to burn more fuel to maintain the same cruising speed. One of the most common offenders are roof bars and luggage racks. Many drivers install these accessories for a specific trip and then leave them mounted permanently out of convenience or oversight. These structures break the laminar flow of the air, creating turbulence and low-pressure zones behind them that act like an invisible anchor. Even when the bars are empty, they can increase fuel consumption by a considerable percentage, especially on the highway. If we add roof boxes or bicycle racks to this, the impact on the pocket is immediate and severe, since the engine must fight against a much larger wall of wind. Reason 11. Brakes slightly seized or stuck. A mechanical problem that often goes unnoticed, even for experienced drivers, is that of brakes that do not release completely. The braking system is designed to apply immense pressure on the discs or drums and then retract millimetrically to let the wheels spin with total freedom. However, due to corrosion, lack of lubrication on the guide pins, or the aging of the brake hoses, it is possible that one of the calipers does not retract enough. This creates a constant friction phenomenon known as brake drag. When this occurs, the car is fighting against itself. It is like trying to pedal a bicycle while someone slightly squeezes the brake lever. The engine must generate extra power to overcome GRU parasitic resistance, which raises fuel consumption silently. A simple way to detect this problem is to pay attention to how the vehicle behaves when we stop accelerating on a flat surface. If the car stops too quickly, or if we feel that it has no inertia, it is very likely that there is a stuck brake component. Another clear sign is excessive heat in one of the tires after a short journey without having braked sharply. Brake maintenance should not be limited only to changing the pads when they wear out. It is vital to perform a cleaning and lubrication of the moving components of the braking system at least once a year. The accumulation of dirt and dust from the pads themselves can block the mechanisms, causing the rubbing to be constant. A braking system in perfect condition ensures that all the energy from combustion is dedicated exclusively to moving the vehicle forward and not to generating unnecessary heat in the brake discs. Reason 12. The human factor and predictive driving. Despite all the technological advances and electronic management systems, the component that most influences fuel consumption continues to be the person behind the steering wheel. The driver's right foot has more power over fuel economy than any mechanical modification. Predictive driving is the art of anticipating traffic conditions to avoid wasting energy. Every time we brake, we are converting the energy we already paid for at the pump into useless heat in the brakes. Therefore, the goal of efficient driving is to minimize the use of the brake pedal through constant observation of the environment. Accelerating aggressively to quickly reach the next red light is one of the most expensive and useless practices. The correct way to operate is to perform progressive accelerations and maintain a safety distance wide enough so that we can adjust our speed simply by lifting our foot off the accelerator when traffic slows down. By using the engine brake, we allow the computer to cut the fuel flow to the injectors almost completely, taking advantage of the vehicle's inertia to keep the systems running at zero cost. Recovering the original efficiency of an automobile requires a systematic approach that combines rigorous mechanical maintenance with a change in usage habits. We have analyzed how everything from a faulty spark plug to poor tire pressure or aggressive driving can destroy personal economy. The action plan should begin with a deep diagnosis of the engine management systems, followed by a review of the chassis elements and aerodynamics. It is not about performing expensive repairs randomly, but about understanding the interconnection between all the components that allow movement.